Hi, welcome to this new video on constructing shear force and bending diagrams of beams, wherein we will derive the fundamental relationship between load, shear force, and bending diagram. To understand this, we are considering the beam, such as the one what we see here, AB, with certain loads acting on them. Our x-axis is fixed here at this left end of the beam. Okay, y-axis is like this. Now, if we cut a section which marks or which measures x units away from the left support, what's going to happen? We have what we call shear force and then bending moment. How do you know that? Because we can construct a simple experiment using an eraser. Take an eraser, mark two lines on the top face. Now, if we flux it, what's going to happen? This is going to change its shape like this. Okay. Now, the two lines will become the ones what we see here. If you consider what's happening to the lines, the top lines come close to each other, whereas the bottom lines will move farther from each other, right? So that's what will happen. What does that mean? That means the top fibers, if you take the same eraser and if you mark lines which are like this and do the experiment, we see that top lines will undergo a reduction in length, the bottom ones will undergo an increase in length. So if one typically assumes plane section remain plane even after bending, what one gets is we get a linear strain profile across the depth of the beam, right? So once you get this, what one can do, one can also get the stress profile as well. How? If we consider Hooke's law holds, what we need to do is we need to take the strain profile and we need to multiply each ordinate with modulus of elasticity, right? So from that we get the stress profile, which also varies linearly, right, within the elastic range. Now what one can do is in the stress profile, one can replace the top distribution, the resultant like this, and the bottom one with the resultant like this. These are LA distance away from each other, right? Which is where LA is the lever arm. So this constitutes what? A couple, which is the resistance offered by the beam. And what we call that, that is called bending moment, right? It literally bends the beam and hence we call it the bending moment. Similarly, one can understand shear force, but we are not explaining here. Shear force is marked by Vx here, right? So now if we cut across any section, there are two portions. We have a left portion and we have a right portion. We are not showing the right portion here. If we just consider the left portion, these two forces must exist for the beam to remain in equilibrium, right? So M of x, V of x exists to establish equilibrium. That is summation of vertical force equal to 0, summation of moment about z axis equal to 0, right? So that's what that presence indicates. Next, what we're going to do is apart from that, we are also considering we're going to consider influenceable element which is located in the right proximity of the cut what we made here, right? So this is an influenceable element that we consider with the length del x, right? However, we are exaggerating the view here. Now, in order to get the expressions, we need to first finalize the notation and in the sign convention. What we call positive shear is if the shear force at the right end of the beam is upward and at the left end of the beam is downward, we call that positive shear. This is bit contrasting to what is in the classical books. Okay, but this is what we follow here. Anyway, this is usual. Whatever the moment, pair of moments which cause sagging of the beam is considered positive bending. That is, at the right end it should be counterclockwise, right? And the left end it should be clockwise. Right? Bear this in mind. We will step further. Now we are going to take the free body diagram of this differential element. We are going to use the equilibrium equations to establish the relation. Right? Mind that the force is considered to be acting upward. Right? However, we see that in the actual beam, the variation is uniformly varying load, right? But when we consider influence element, what we can do is we can approximate that as a distributed load of same, uniform magnitude, right? So that's what we are doing here. Now consider summation of vertical force equal to 0. That means downward force equal to summation of upward forces. The upward forces are this, right? Vfx plus del x, and then the one due to the externally applied load. Now, in the same manner, what we can also do is if at the left end the bending moment is marked as mx, and the right hand should be m of x plus del x, right? And also we need to bear in mind that at this interface, right, when I made the cut, I'm marking this and this as per the positive sign convention what we are adapting, right? When we draw this portion which is available at the right proximity, right? I can't even say right proximity, which is just right to it. The pair should be of same magnitude but of opposite sign. Okay. So those things should have been told. Just I am saying that. Now coming back to this expression, what about V of x plus del x? What does that mean? What does that even mean? That expression should be further expanded using what we call Taylor series expansion. Okay, so the Taylor series expansion for f of x is as follows: what we see here, f of x is equal to f of x naught plus f prime of x naught and so on. That is, if we know the value of function at a location x naught, the value at x is given by this expression. Okay, let's say del x is given by x minus x naught. Okay, that is x minus x naught is given by del x. So we can rewrite this expression as, for x we can write what, x plus del x, right? I mean x naught plus del x, and the RHS x minus x naught is replaced by del x and so on. So once you know the value of the function at x naught, at x plus x naught, the function's value is given by this expression now. Okay, that's what we are concerned about here. What is the value of shear force given that v of x is known? Okay, so then we can write the expression for v of x plus x naught using this expression, which is v of x, right? And then the derivative into del x and the higher order terms which are given here. Now we are going to ignore these terms, just we are going to take this expression. So in this expression for v of x plus del x, we are going to use what we have in the right hand side up to this, I mean first two terms. Substitute them here. Now these two terms cancel with each other. What remains is this. Now when we rearrange that, we get dv by dx equal to minus q. Okay, this one other term which relates the shear force to the intensity of load applied on the beam. What next is, we are now considering the summation of moment about this axis 0, which ensures the moment equilibrium. Now I am going to take the sum of moments about this point. Again, clockwise moment equal to sum of anti-clockwise moment. The only clockwise moment is this, and the other anti-clockwise moment are due to the other forces, such as this, and then this. This is straightforward. You can do it yourself. But what one needs to understand here is we are again going to ignore higher order terms, this and then this, which contains del x square, right? And apart from that, these two terms cancel with each other. From what remains, we get the expression dm by dx equal to minus v. Okay, this expression relates the variation of bending moment to the shear force. To summarize, these are the two expressions that we obtain using the inference element, that is considering the equilibrium of that element, which says dv by dx equal to minus q and dm by dx equal to minus v. Mind that we have an active sign in both these expressions, right? Right? And then these are the positive signs of internal force that we are adopting here. I'm not repeating it here, just have this in your mind, right? Now we are going to take this particular expression and we are going to integrate it onto, we are going to see what does it mean. Okay, so this is the first expression what we derive. Now I am integrating between the limits xl and xr. Xl is the location at the left hand and xr is the location at the right hand, let's say. Now after integrating, you can rewrite this expression because this becomes v xl xr, so upper limit minus lower limit we put, and I'm taking the v of xl to the RHS, right? So that's what I'm doing here. From that I'm getting v of xr as this. What does this expression say is, if we have a beam with v of xl known at the left hand, that is shear force known at the left hand, if one needs the shear force at the right hand with the given load on the beam, what one's supposed to do is, we need to take the shear force out to the left hand, and to it we need to add this quantity. What does this quantity say? This is just a definite integral. What does a definite integral mean? It means the area under the curve, right? Here the function is what? Q of x. That means it says that if you want to know what is the shear force at the right end, all that you need to do is take the shear force at the left end. Okay, take the shear force at the left end, and to that add the area of the loading function. Okay, area under the loading function to this VXL, that will give you the value of shear force at the right hand. Okay, the same logic applies to this expression. You can integrate it and to get, and you will finally get this expression. This again says if we want the value of bending moment at the right hand, you take the value of the bending moment to the left hand. To that you add the area under, which one? Area under the shear force diagram. Okay, that's what it says. So one can approach, or one can draw the SFD in BMD using the area under the curve approach. Okay, or one can also use this expression as such, and one can relate it to the derivatives. Okay, slope of the tangent. So I'm going to combine both of this to construct the acceptance VMD of a beam element what I have here, which is loaded with an UDF. Okay. Now suppose that you know what is the value of VB, right? I'm going to draw first the SFD, right? Now I'm starting with the value of VA here. Okay. Here it is left side down, so should be positive. I'm marking it up, right? Now there are two ways in which we can draw it. Either we can use this approach, area under the curve. I will use that as well here. Now say that if I want VB, what I should do? VB will be equal to VA plus, there should be a negative sign, right? VB equal to VA minus integral Q naught dx, okay, XL, XL, right? Mind that in our case, this Q naught will contain negative sign because the force are acting downward. In the original derivation, I told that the force are acting upward, right? So here, as it is acting downward, I should consider another negative sign, right? Therefore, VB will be equal to minus of minus Q naught dx, okay, plus V. That is, if I want VB, take the value of VA, to that add the area under this, right? So the area under this will boil down to Q naught into L, right, plus V. Therefore, VB should have a higher value because you have Q naught into L plus VA. Therefore, VB should be more. Okay, that's why I'm asking whether VA should be greater than VB or otherwise, right? So VB should be greater than VA to satisfy this particular expression, right? That's the one way in which you can interpret and draw the SFD. Other way is, say that in most of the cases we know the reactions at the both ends, that is reactive force and reactive moments. Let's say that I know V and VB a priori, right? And I know that VB is greater than VA. Now the question is how we are going to connect these two ordinates. Okay. So here in this case, it's straightforward. Once you know V and VB, the only way is connecting by a straight line. But it should be only a straight line and can be a curved one. Okay. Supposing that it's a curved one, what is the problem? Now it's a curved one. This expression says that the derivative of the shear force diagram at every location should relate it to the negative value of the ordinate of the load diagram, right? If it's a curved one, the problem is we take a particular point here and draw the tangent. What is happening is the tangent will have a particular value, right? But if I draw the tangent and find the slope at every point, it says that if I consider a curved line, the slope is constantly changing, right? Constantly maybe increasing here in this case if I draw like this, right? But will that satisfy the requirement that d by dx equal to minus q? No, because if that is constantly changing, this can't be the load here, right? Then it has to be constantly increasing here. The intensity should be constantly increasing, but that's not the case, right? Here I have a constant wheel. That means the slope of the shear force diagram should also be a constant. When can it happen? Only if it's a straight line. That's the reason why we got to connect these two ends by a straight line. Now, how can I measure the slope? I am going to measure the slope using, uh, with respect to the positive x-axis. Whenever I measure the slope with respect to positive x-axis in the counterclockwise direction, it's going to be a positive slope, right? Now I see that the slope is positive, right? And it's a constant one, right? That should match with minus q. Here, what is minus q? Minus, as the force is acting downward, this is minus q naught, which is q naught, right? This is a constant, it's positive as well, right? So the positive slope at every location, you can take the slope at any location that should match with the negative value of q naught. Okay, that's what is happening here. We have a constant slope matches the constant density of loading here, okay, and other things what I described here. And let's move on to the bending diagram next. Again, let's say you know the value of MA and MB. Okay, you know the value of MA and MB, which is the case most often, right? Now the question is how we want to connect these two ends. Should it be with a straight line? What's the problem with a straight line? If I start with, if I have a straight line, the slope of straight line is a constant, which means the shear force diagram will have a constant ordinate throughout, right? So if you have a straight line, that means then the shear force diagram should be something like this with constant ordinate everywhere. But here I have a shear force diagram with its ordinate constantly increasing, right? Which means I should have a curved line here. Only if I have a curved line, the slope will be constantly changing, right? So will this line be fine then? What's the problem with this? The problem is if I have a line like this, if I draw a tangent at any location, we see that the slope of the tangent drawn at consecutive points will be constantly decreasing. Slope will be decreasing, but it's not going to match with the shear force diagram. The shear force diagram, this shear force diagram as its ordinate is constantly increasing, right? Therefore, if I draw this line, it is not going to hold true. Okay? Therefore, we need to connect these two ends with this with a line like this. For instance, if I take a point here, if I draw a tangent, and then if I get the slope, mind that I am measuring it clockwise, which means it's a negative slope, right? Then I have a negative slope here. Okay. Now this slope with a negative sign, because I can rewrite this as minus dm by dx equal to v, right? The slope with a negative sign should give me the value of the ordinate at the same location, the shear force diagram. Okay, I have a negative slope here. If I add a negative sign to that, it will be positive. Okay, that should give me the value of the ordinate at the same location, the shear force diagram. That's what is happening, right? So at different locations, I can draw that and find the slope. We see that what is happening, the slope is constantly increasing and it's a negative slope. Okay, so I need to add a negative sign to that minus dv dm by dx, which will give you a constantly increasing ordinate in the shear force diagram. Okay, that's what this expression reads here. We see that it's constantly matching. So that's the way we see what should be the trend. Okay, that means whether should I draw like this or should be a straight line or should be this. So you can use this expression to relate the SFT to the BMD. But this is not the only way. I'm going to explain the other way also briefly. The other way, which is called directly, by the way, this I'm calling differential relations based approach because I'm trying to draw qualitatively using these expressions. Okay. But in the other approach, which is based on equilibrium, which I call direct equilibrium approach, what one does is we need to cut a section, typically at a distance x meter away or x units away from the left hand, show the shear force and minimum like this in the positive sense, write the equations for shear force and then minimum using the equilibrium conditions. Summation of vertical force equal to 0 will give upward force equal to sum of downward force. The downward force are this and this. You see that this matches with the expression y is equal to mx plus c. Okay, what is mx plus c? It's the equation of a straight line where m is the slope and c is the ordinate of the x-axis, right? Sorry, y-axis. So we have this x-axis here and y-axis here, right? At the left hand, right? So here we see that the shear force diagram has its ordinate VA and then slope M, M equal to Q naught. Okay, that's what this expression says. So draw this straight away and it gives the shear force diagram variation, right? What are the minimum diagram? Now to get the minimum diagram, take the same FBD of the portion what you have, write the moment equilibrium equation, and from that you need to the moment equilibrium equation says that summation of clockwise movements equal to summation of counterclockwise movements. Once you write that, get the expression for m of x as I'm doing here. For this particular case, you get this expression what you see here. Now you see that this is synonymous with equation y is equal to x squared plus bx plus c. What does it say? This is the equation of a quadratic parabola, that is parabola of degree 2, right? Therefore, if I know the ordinates MA and MB at both ends, I need to connect these two ends using a parabola, right? But the question is whether it should be a upward parabola or downward parabola, I mean convex upward or convex downward. It should be dictated by the sign of the coefficient which is there with the highest degree. Okay, here the highest degree is x square. The coefficient here contains a negative sign, which means the quadratic parabola in this case should be opening downward rather than being upward. If I see, had I contained an expression, had I had an expression something like this, the other signs doesn't matter. Here, if this is a positive sign, it will be a parabola which is something like this. But however, I have a negative sign here, which means the quadratic parabola should be opening downward. Okay, and that's the logic with which we draw this minimum diagram like this. You see that these two diagrams match with what we obtained here, right? The same ones. However, if you want to quickly draw a qualitative SFD and BMD, this method goes handy. Okay. So therefore, in the upcoming videos, what we're going to do is we're going to explore this method deeper. Okay. I mean, we'll introduce certain thumb rules with which we'll learn how to draw SFD, how to construct SFD and BPMD using these two expressions in a faster manner. Okay, that's what we're going to see in the upcoming days. Hope this helps. Thank you so much for your passion listening. We'll meet in the next video.